So hello everyone. In the last session, we have seen the different things, like we have seen about the flux, and we have seen the relation between the plane angle and solid angle, and also we have learned that how learning the solid angle will help us to solve the question in a very easy manner, in a very simple steps, without going to much integration and and all that thing that we have learned. Now in this session, we are going to start with the conductors, and we will see what are the different properties of the conductors. And yesterday I have given you some idea about the conductors, like what we are going to discuss. So first, before starting a conductor, you should have idea about equipotential surface. So first I will try to explain you about the equipotential surface and give some of the properties of equipotential surface, and then we move toward the conductor. Clear? So we are almost about to reach the end of the chapter. Okay, so let's start. First we will go with the small topic, that is a very small topic, not a big topic, that is equipotential surface. Okay, what is equipotential surface? Okay, that is our first topic. What is the equipotential surface? So let's start. See, equipotential surface, from name it is clear. Equi means equal and potential means you know. So equipotential surface means the surface on which the potential at every point is same. Okay, the surface, it can be any type of surface, 3D, 2D, any type surface on which potential at every point is same. Okay, that is called as the equipotential surface. Okay, clear? Okay. Next thing is that, so if I there, for important point one, for a different charge distribution, we have for a different charge distribution, we have, you can say, different equipotential surface. We will see in some examples also different equipotential surface. That is the thing. Means for different charge distribution, we have a different types of equipotential surface. Clear? Now let us see some of the examples on this. Example number one. Suppose I have a point charge. Okay, Q is there. So can you tell me what will be the equipotential surface? Can you tell me what will be the equipotential surface? It will be a, in spite of drawing this, I can draw this. Okay, for a point charge, the equipotential surface be a sphere, correct? It will be a sphere, because if you see at every where the distances are, and what will be the potential at every point on this surface, that is kq by capital R, correct or not? So if I write the potential at this point also, it will be same, kq by capital R. So I can say it is an equipotential surface for a point charge, and it doesn't mean that this is the only one, basically this is the only one sphere. No, we can draw multiple spheres like that also. This is also a equipotential surface. Okay, this is also a equipotential surface. If you can see, only the difference is the radius is smaller, but at this surface, on this surface, if the potential will be kq by some small r. Okay, if suppose the radius is smaller, here also the potential at this surface will be kq by small r. So what does it mean? The meaning is very simple. Equipotential surface means a surface on which the potential at every point is same. So for a point charge, so from here I can say for a point charge, the equipotential surface is a concentric spheres. Correct? It is a concentric spheres. Simple. Clear? Okay. Let's move to some more example. Suppose I have a linear charge density. Suppose my charge density is linear. Okay. I have a linear charge density. Okay. So suppose this is my charge density I have. Okay. Suppose I have a linear charge density. It is lambda coulomb per meter, means the positive charge is present on this wire and it is an infinite long wire, correct? Like this. So if I ask you what will be the equipotential surface for this, try to think what will be the equipotential surface for this. For this surface, can I say equipotential surface is going to be a cylinder? Yes or no? Equipotential surface will be going to be a cylinder. And is it only one cylinder will be there, or there are infinite many cylinders? So there are infinite many concentric cylinders will be there, like this. Okay, there are the infinite many cylinders will be there. So for infinite long wire, the equipotential surface is a concentric cylinder. Correct? So for an infinite long wire, the equipotential surface is going to be a concentric cylinder. Clear? Now let us take dipole. This is the example number 2. Okay. Next example I am drawing here. So for a dipole, let us take one minute. Okay. Yeah. So let us take a dipole. You know dipole. So for a dipole, can you tell me what will be the equipotential surface? So first let draw a dipole. Okay. First let's draw a dipole. For a dipole, we have plus q and we have a minus q. Correct? Okay. Can you tell me what will be the electric field lines? I tell you the electric field lines also. This will be like this. Okay. Correct. Like this. Is it correct? Tell something whether it is correct or not. See, whenever in the class you will speak, you will not sleep. We are speaking, but we are behind the camera. Then speak loudly. So this is my surface. Okay, this is my surface. Clear? Now for this surface, if I want to draw equipotential surface, how it will be look like? Let's see. If for this charge, the equipotential surface will be like this. So this will be my plus q and this will be my minus q. So equipotential surface is here, and for these lines, okay, for these lines which you are seeing here, for these lines the equipotential surface will be like this. You will find it like this, okay, like this, correct? Are you getting my point? What will be the, how the electric field, like equipotential surface will look like? Okay, are you getting? I hope you are understanding what type of equipotential surface it look like. This is a NCRT question also. In NCRT they have asked you the draw the equipotential surface for the dipole. Correct. This is how you will see the equipotential surface for a dipole. So I hope with all this example at least you get an idea about the equipotential surface. Equipotential surface means that is the surface on which the potential is same, and how to draw the different diagrams for a given electric field lines, or you can say how to draw the for different charge distribution, how to draw the equipotential surface. We will understand in more better way, okay, how to draw the basically the how we have to draw the that surface, how we can easily draw that surface. We will understand when we know the property of the equipotential surface. So let me start with the properties of a equipotential surface. So let me start with the properties. Property number 1. Correct. So what is the first property? The first property states that the equipotential surface, the potential difference between 2 points on P on an equipotential surface is 0. Is the potential drop between the 2 point on equipotential surface is 0. That is the first thing. Why? Because it is a equipotential na. So suppose if the potential will be same at everywhere, if you obtain the difference between the potential between the 2 points, it will be always 0. That is a common sense. Second thing, the work done by external agent or electrostatic force, okay. So the work done by external agent or electrostatic force on moving a charge q naught on equipotential surface is 0. How? If you remember, work done by the external agent is equal to VA minus VB divided by, correct? Now if this thing is 0 for equipotential surface that we have seen, if this quantity is 0, this thing is 0, so obviously the work done by external agent is equal to 0. And we know, I given you a relation also, that is work done by the external agent is equal to minus time of the work done by the electrostatic force, correct? If this term is 0, obviously this term will become 0, correct or not? So that's what, if you are moving any charge on a equipotential surface, then it will be always, the work done will be always 0, whatever type of thing you are taking, whether it is an external agent or whether it is an electrostatic force. Clear? That is the second point which has to be clear. Clear? Any doubt? Okay, let's move to the third point. The third point is that the direction of electric field is always perpendicular, or let me move it to the next page. Let me move it to the next. What is the next point? The direction of electric field is always perpendicular to the surface. Okay, the direction of the electric field is always perpendicular to the surface. That is the second property. Third property means, what I am trying to say, suppose if you see all the diagram, you will understand. Let's see here. In this case, if you can see, you will understand better from here. See, the electric field lines will be like this, correct? And the electric field lines like this. So you can see my equipotential surface and the electric field lines are perpendicular to each other, correct or not? See, all are perpendicular to each other. That is only the property. Basically what I am trying to say, the electric field, like basically your electric field lines are always perpendicular to the equipotential surface. That is a simple point. Okay, so if I give you, suppose if I give you electric field lines like this, so can you draw the equipotential surface for it? I hope you can draw. Suppose my electric field lines are like this. Okay, now you can easily draw the equipotential surface. How? Because the equipotential surface should be perpendicular to the electric field lines. Should be perpendicular to the electric field lines. So how will you draw? Obviously, my basically my equipotential surface will be like this, correct? Yes or no? So my equipotential surface will be like this. It will be like this. Are you getting my point? I am trying to say it will be something like this. Okay, let me draw properly so you will understand it better. So my equipotential surface will be something like this. Okay, it will be something like this. So it is perpendicular to the surface. Okay, if you see, it is always perpendicular to the surface. If you see properly, it will be always perpendicular to the surface. Okay, means it will be this surface is like this, correct? So the electric field lines and equipotential surface are always make a 90-degree angle. So if it is like this, if I ask you what is a close integral, if you remember the formula, I given you one formula, that is dV is equal to minus E dot dr. So if my E and dr both vector will be perpendicular, obviously, because my surface is like this and my E vector is like this, so this will be, and leave it. You know, that is equipotential surface, the potential difference will be 0. If the potential difference is 0, that means this quantity will be 0. So this quantity has to be 0, correct? What do you get for idea from this thing? dV means V final minus V initial should be equal to 0. So that means why V final is equal to V initial. That means potential is always constant. And that is what is the definition of equipotential surface. It has to be always constant. That is why we are saying E dot dr should be 0. And that is why the electric field should be perpendicular to the surface. Then only my E will become perpendicular to dr vector. That is the reason, correct? Any doubt here? Okay. Next property we have, that is next property. What is the next property? Wait a minute. What is the next property? Next property state that the two equipotential surface never intersect each other. That is the next property. Okay, the two equipotential surface can never intersect each other. If they intersect each other, then what is the problem, sir? Suppose I have a one equipotential surface like this, and suppose I have another equipotential surface like this. I don't know how it is, but they are the two equipotential surface. So at this point, the electric field should be like this for this surface one, and for this surface, the electric field should be like this, because it should be perpendicular to the surface. Now, so this is for second surface, correct? So at 2 point, if you are seeing, we are getting at 2 point, at 1 point we are getting two directions of electric field lines. This is my E1 and this is my E2. So is it possible at a 1 point we can have a two direction? Answer is no, it is not possible. So that is the reason the two equipotential surface can never intersect each other. I hope it is clear, just note it down. Clear? Done? Okay. So what we have understand till here, that is what is equipotential surface and what are the basic properties of the equipotential surface, that we have understand here. Okay. So let us now move toward the next thing, that is called as a conductors. Now we are going to learn about the properties of conductors, because from here we get some basic idea. And remember, very important point you have to remember, that equipotential surface means the potential will be same everywhere. It doesn't matter where you are talking about, but the potential has to be same everywhere, okay, on the surface. That is a property of the equipotential, and that is a very important property. And second property, the electric field lines are always perpendicular. One more thing, if you remember one more relation we have, that is my E vector is equal to minus dV by dr. I am writing in short form, but it is a big expression, but I am writing in short form. So if it is like this, so can you tell me, if the potential of this surface is 100 volt, what is the potential? It will be greater than 100 volt or less than 100 volt? You can see here, there is a minus sign, means when we are moving in the direction of electric field, the potential is going to decrease. When we are moving in a direction of electric field, the potential is going to decrease. This minus sign indicates that it's a very crucial point when, or you can say potential, very important point, potential decreases in direction of electric field, correct? So if it is 100, then it will be less than 100 only, that is 80 volt. And if it is 80, then it should be less than 80, that suppose let us take 20 volt, like that. Means it cannot be greater than 80, that is not possible. Here it cannot be greater than 100, that cannot be possible. So that is the case, okay? So these are the property. I hope you understand about what is equipotential surface and what is the basic idea of equipotential surface. Now from here we are moving toward the next thing, that is the properties of conductors. That is our major portion, and we are moving to that topic only, I think. So properties, give heading properties of conductor. We will see each and every property, and you have to remember this lecture as it is, as I am teaching, as I have remembered it. Okay, everything should be in your notes and every point should be in your note, because it is, I will going to write each and everything. Already I am writing each and everything, but I am going to write each and everything, not a single point I will miss. Okay, because it is a very important, and if the question will come, it will directly come from the notes. There is a no other way, other place they can ask the question. Okay, just note it down whatever I am telling. Okay, we can start now. So let us suppose we have a conductor. I am drawing in 2D, okay, not in 3D. Just take it as a sphere, okay. The conductor basically. So suppose you have my question is that suppose it is a sphere or a conductor. It is a conductor. Suppose conducting sphere, basically conducting sphere. So it has a free electron, correct? Suppose my first question is that you have to answer me small question. Suppose I have given a charge q to it. Okay, I have given a charge q to it. Correct? I have given some charge q to it. What is going, where this charge is going to be present, whether it will be present here or whether it is present here or whether it will be present inside. My question is that where it will be present. Just think and then tell me. Just first think and then tell me where this charge will be present. Are you understand my question? What I am trying to ask? Okay, I have given a charge to this sphere. This is a conducting sphere. Where this charge will be present? See, there will be material inside this conductor. Obviously, it is not hollow. It has some material. Correct? Okay. Let me donate this material by. Suppose it has some material. Okay. Suppose it is a material. It is a material inside the conductor. Correct? I have given a charge q here. Okay. It is a material that is present inside the conductor. If I take, suppose if I take a very small Gaussian surface just inside the conductor, just inside the conductor, very small, like just inside the conductor. Okay, just I have taken a Gaussian surface. This is my Gaussian surface. I have taken a Gaussian surface. Okay, basically what is going to be happen, let us try to understand the picture. See, when you, there is a free electrons are there. Okay, initially it is in a stable condition, there is nothing is there. When I keep this, given this charge to the conductor, what is going to be happen? Just think, what is going to be happen? Just try to understand. Okay, the picture. Okay, step 1. Basically I am trying to let you understand the things in simple steps. Okay, suppose basically what will happen initially, just try this complete thing in very simple way. Suppose initially initially it is at equilibrium, everything is stable. Initially it is at this condition, the total charge is, when you bring the charge plus q here, what is going to be happen basically? When you bring this charge plus q here, what is going to be happen? There will be some negative charge will induce in this surface, correct? And there will be some positive charge induced in this surface, correct? Where is the charge induced is equal or different? First you tell me whether the charge induced here the equal amount of negative charge or here equal amount of positive charge will induce. Answer is no. Sir, as the distance is less, so force will be, electric field will be more. So the more negative charge will be induced here. There will be more negative charge, correct? That is obvious. From our common sense, we can tell, more negative will be there, but less positive will be there. But the overall, this conductor will be charged or neutral. Overall, conductor will be neutral because the total number of electron and total number of positive charge, both are initially it is neutral. So after just placing the charge here, the charge will induce, but the total charge will be remain same only because charge is always conserved, that we know. So total charge is still 0. If you see the total charge is still 0 only. Okay, but due to q there is charge induced. I am going very slow, okay, but just try to understand. Okay, the charge will induce. Okay, correct? This thing is clear till here. Okay, so if the charge will induce, there will be internal electric field will be there. If you see from here to here, we have E internal like this, correct? And similarly, due to this plus q, there will be external electric field will be also there. And if my E net will be how much? That will be E external plus E internal. correct or not? I writing in a vector form, okay. Not equal to 0. If this is a condition, okay, if it is not equal to 0, then what will happen? Then what will happen? The whatever the electrons, because the electrons are present inside this conductor now, there will be some force experience on this electron, correct? So there will be some force experience on this electron. So this electron will try to move, this electron will move, and it will try to make the conductor neutral. It will try to move in such a way that it will try to make the conductor neutral and make the total electric field equal to 0. Okay, then force experience by electrons of, because that is because the conductor has a free electrons, na, because a force experience, then a force experience by electrons, not of, the force experience by electrons. So they move in such a way to make E net equal to 0. So finally, steady state, at a steady state, what will happen? At a steady state, you will see steady state, my E net will be, so this is the thing which is going to be happen when you going to bring a charge on this, means my total internal electric field will automatically will become 0. So what we understand that E net will be always 0 inside electric field will be always 0 inside, correct? If it is true, now you tell me, by Gauss law I can say my phi is equal to E dot dA, correct, into Q in by epsilon naught. Now as my internal electric field is 0, I can say my Q inside will be also equal to 0, correct? So that means if we are going to give this charge to the conductor, this charge will always going to be present on the surface of the conductor, means this charge will going to be present only on the surface, okay, only on the, there will be no charge inside. What is the reason? You understand, the reason is very clear. And this process, this whole process is happened within fraction of second, within, like, it happened in 0.00000, like in very small time, even you can't think about that time, that much within this duration this whole thing happened. So whenever you give a charge to any conductor, it will always present on the outer surface of the conductor, that is fixed. It will be always present on the outer surface of the conductor, it will be not reside anywhere. So for example, I hope the picture is clear. For example, let's take one more example and try to understand one more thing. If I ask you, let me ask you one thing. So suppose if the picture is clear, then you can answer me this question also. If suppose I have a two concentric spheres and two concentric sphere, correct? Yeah, suppose I have a two concentric spheres, and inside it is hollow, this thing is hollow, okay, correct, this thing is hollow and it is given. Suppose now I have given a charge q. Now you tell me where the charge will be present, whether it is present on the outer surface or the inner surface, where it will be present. Just use your common logic, common sense, which I have told you, and you tell me where the charge will be present. Okay, see, one thing is clear, that is net electric field inside will be 0. That is true, correct or not? E internal will be 0. So here I am sure there will be no charge inside. Now if I take a Gaussian surface here also, because the doubt is here only. If I take here also, because it is a material, correct or not, here also the free electrons will be there. So here also the electric field will be, because electric field is 0 na, inside whole this thing electric field is 0. So that means again my q in will be 0 here also. So that means it doesn't matter whether you have a ring or something else, this charge will be always present on the, it will also reside on the surface only. So this charge will be present on the surface. That is always true. Correct. Have you understand the concept? Means whenever we give any charge to any conductor, it will always reside on the outer surface of the conductor. That is a conclusion point. So our conclusion point will be that when we give charge to any conductor, it always present on outer surface of the conductor. Correct. Just note it down and tell me if anyone have a doubt. Correct. Completed. So that is the first property we have understand. Okay. Any doubt is there? Now next move to the second property. Second property. What is second property state? First property is clear to everyone. I am going very slowly because this topic is very confusing for the students. Okay, and it's a JEE advanced famous part, and the JEE mains also famous thing, and for NEET also it is a famous part. They always ask one question from this. So just if you have any doubt, please tell me. Okay. Next, move to the second property. What is the second property say? As I told you, as I told you, one picture is very clear that what is that? Sir, the electric field inside the conductor will be always 0. That is always true. Okay, it is always true. That is the electric field inside the conductor will be always 0. No doubt. Okay. So if the electric field is 0, what I told, it will if the electric field is 0, I can apply this formula, correct? dV is equal to minus E dot dr. If the electric field is 0, this term is 0, I can say my potential is equal to constant everywhere, correct or not? Say yes or no. Everywhere inside, not outside. Okay, everywhere inside, correct? So can I say it is a equipotential surface? It is a equipotential surface. So if I ask you how will be the electric field lines for this conductor, it will be something like that. It has to be perpendicular to its surface. If you see the electric field lines, it will be something like that. Correct? It will be something like that. Means the electric field lines are, I have not drawn it properly. Let me draw. The electric field lines are always perpendicular to its surface, and it will behave as an equipotential surface inside. Inside my potential will be, it's not visible, let me write with some other color. My V will be constant and my E inside is equal to 0. Okay. Okay, sir, I understand the potential will be constant, but what will be the value of that potential? So just there is a proper derivation for this, but for now, for understanding, I am telling you the formula, but we will see the proper derivation and understand it, because it is very important for the J advanced point of view. So we will understand the form, like just for now I tell you, if suppose the radius of this conductor is r, okay, then the potential, okay, then the potential inside will be always, suppose the charge given is q, will be always k q by r, correct? This is the potential, and the potential at the surface of the conductor will be also equal to V in. This is coming from the derivation that I will tell you when I will teach you, but just now you remember this, the potential inside at any point, here, any point, okay, it will be always kq by r, and surface also it will be kq by r. Clear? Any doubt here? Okay, I think kq by r square, sorry, not r square. Clear? Please note it down. Completed? Okay. So let us take some example and try to understand the some things in better way. Clear? Let us okay. Suppose we have a conductor, okay, and suppose I place the capital charge Q here, okay, and the distance from the center is, let me draw properly, look like it is. Suppose the distance from the center, this is my center, and the distance from the center is d, correct, and the radius is given, the radius is r, correct? Okay. So if I ask you one thing, obviously when you will give a charge to this surface, it will be like, basically when you bring a charge here, you know that there will be some negative charge, there will be some negative charge will be induced here, correct or not? There will be some negative charge will be induced here, and some positive charge will induce here, correct? I want to know what is the total potential at the center. First tell me, what is the electric field inside? What is the inside electric field? First tell me this thing, what is the inside electric field? It is still 0, yes or no? Electric field will be still 0, that we have seen, because the steady state is reached. Okay, now what is the potential at center? Can you tell me what is the potential at center? This charge is kept here. What is the potential at center? One thing is clear, that is potential at center will be due to two things. Potential at C, potential at center is due to this Q, and potential at center due to the induce, correct? But we have seen one thing, that this total charge will be always equal to what? This total charge which is induced will be always equal to 0. That's total. See, the distribution is not equal, but the sum of this total charge will be 0 now, because initially the total charge on this conductor is also 0, and charge is always conserved, so it will be 0. So if the total charge is 0, so obviously the potential due to this positive charge is plus, and the potential due to negative charge will be minus, and they are both are equal in amount, so obviously this thing will be 0, correct? So what is the potential at C due to Q? That is potential at C due to Q, we know that is K. Potential due to charge at distance D, we can write KQ by D square, or KQ by D. I think I have given a wrong formula. It is not a square. It is KQ by 1 minute. Yeah, it's not a square. Sorry, I did a mistake. sorry. So let me check that also. Okay, I have 1 minute. 1 minute. Just give me 1 minute. Yeah, it's correct only. There it is correct. Yes. Sorry. Yeah. So our potential at C will be this much. I hope it is clear now for you. Correct? Any doubt? So let me add one more thing here. Suppose in the same question, I ask you one more thing. Let's take this another example. Suppose this distance is small r. If at this point, and suppose this point is A, the electric field is at A would be what? Now you tell me, what is the electric field at A? Again it will be 0 only because it is internal point, correct? Okay, now if I ask you, what is the potential at A? That is my question. What is the potential at A due to induce charges? Because the charge will induce. Now I want to know what is the potential at A due to induced charges. Whether it is 0, answer is no. Why? Because this is a symmetrical point, na? This is center, but here it is not a center. So there will be more potential due to positive charge, and there will be less potential because the distance is not same. So we can't say it is a 0. So how you can, like, how will you say what is the potential at A due to the induce? How will you say? How will you calculate? How will you? See, one thing we know, the potential at A will be equal to potential at C, and potential at A is due to two things. One is the potential at A due to Q, correct? And one is the potential at A due to induce. That is also correct. And this quantity we know that this quantity is KQ by T. That is we know. Now what is the another thing we have to calculate? We should know about the potential at, we have to calculate potential at A due to induce. Correct? Potential at A due to induced. That is the thing we have to calculate. That will be nothing but potential, that will be nothing but KQ by T minus potential at A due to Q. What is the potential at A due to Q? KQ, what is the distance? This will be KQ by root over of D square plus R square. I hope you understand the thing what I am trying to understand. Just see this and digest this for a 1 minute. Okay, just see this and I try to digest this. It is clear? Shall I erase this? Clear? Okay. So in this session we have seen properties of conductor and we have seen about the equipotential surface. In the next coming session we are going to see about more properties, and then we are going to see the derivation regarding the conductors, hollow conductors and solid conductors, and then we will solve most of the examples based on the spherical cell, which is a favorite part of JEE Advanced mostly. So the next coming topic after this, whatever the session I am going to take, that is purely for JEE Advanced student. So who is preparing for NEET, just they can skip this next sessions. If they want, they can follow from the after that, they can follow the other session after that. Okay, till then take care, goodbye, like it, subscribe it and share it. Thank you.